We're going to do a simple problem in collisions involving conservation of momentum and, in one case, conservation of energy. This is chapter 10, number 42 from the textbook. And in this problem, a ball with a mass of 100 grams traveling at 10 meters per second collides head-on 10 meters per second and has a mass of 100 grams, which is 0.1 kilograms, collides head-on with ball 2, which has a mass of 300 grams and is initially at rest. So that's 0.3 kilograms, and its initial speed is 0, and they collide head-on. So that's the situation before the collision. And the question asks, what are the final velocities of each ball if the collision is perfectly elastic or perfectly inelastic? So we'll start with a perfectly elastic case. Perfectly elastic collision. And in a perfectly elastic collision, that means kinetic energy is conserved. So the kinetic energy after the collision is equal to the kinetic energy before the collision. Final kinetic energy equals the initial kinetic energy. So that means 1/2 m1 v1f squared plus 1/2 m2 v2f squared, that's the final kinetic energy of each of the two balls, equals the initial kinetic energy, which is 1/2 m1 v1 squared. That's the initial kinetic energy of ball 1, and ball 2 initially is stationary, so it has no kinetic energy. So this gives us an equation where we're looking for v1f and v2f. We know m1, we know m2, we know v1, the velocity of ball 1 before the collision, but that's just one equation with two unknowns. However, in every collision, whether it is elastic or inelastic, momentum is conserved unless there's outside forces acting on it, which is not the case here. So the final momentum equals the initial momentum, which means m1 v1f plus m2 v2f equals m1 v1. That's the momentum of ball 1 after the collision plus the momentum of ball 2 after the collision equals the momentum of ball 1 before the collision, and there is no momentum for ball 2 before the collision. Now, when so now we have two equations. The kinetic energy equation is conserved since it's an elastic collision. Momentum is always conserved. So we have two equations and two unknowns, v1f and v2f. So we can solve this algebraically. The book has already done this for us, and I don't want you to worry about going through the algebraic steps. If we look at the end of chapter 10, in perfectly elastic collisions, when both mechanical energy, that's kinetic energy, and momentum are conserved, and if object 2 is initially at rest, then we can immediately get the final velocity of the two objects. So these two equations combine to give us v1f equals m1 minus m2 over m1 plus m2 times v1, the initial velocity, and v2f is 2m1 over m1 plus m2 times v1. So we can put in our numerical values for m1, m2, and v1, and we get, for the final velocity, m1 minus m2 is minus 0.2, so that gives us v1f is minus 0.2 over 0.4, or a total of 0.5 times v1. So it gives us minus 5 meters per second. That means ball 1 bounces back, and v2f is 2m1, which is 0.2, divided by m1 plus m2, which is again 0.4, so that gives us again 0.5, so that gives us plus 5 meters per second. Let's do a sanity check here on these answers just to make sure momentum is conserved. Before the collision, the total amount of momentum is m1 times v1, that's 0.1 times 10, or 1 kilogram meter per second. after the collision, according to these results, our momentum is m1 times v1f. That's 0.1 times minus 5. So our p1f is 0.1 times minus 5 is minus 0.5. And the momentum of ball 2 after the collision is 0.3 times 5, which is 1.5. It's all kilogram meter per second. And what did this add up to? 1.5 plus a minus 0.5 gives me 1. And so yes, in fact, momentum is conserved. It's just an easy sanity check to do since momentum is so easy to calculate compared to kinetic energy. Part B of the problem asks if it is a perfectly inelastic collision. And in a perfectly inelastic collision, this means V1F equals V2F. In other words, the two objects stick together after the collision. So after the collision, we have this coupled object moving at some V final, and it has a mass of 0.1 plus 0.3, or 0.4 kilograms. And we need to find what's that final mass. So in this case, kinetic energy is most definitely not conserved, but momentum is conserved. And so we have P final equals P initial. P final is 0.4, the two balls stuck together, times V final. That's what we're looking for. And P initial, we already figured out from part A, is just 1 kilogram meter per second. So V final in this case is 1 divided by 0.4 kilograms, which is 2.5 meters per second.